Welcome to the lecture on graphics hardware given within the lecture series on computer graphics at KAUST. A graphics hardware is an additional piece of hardware which we use daily for calculating graphics intensive applications. There have been over the evolution of graphics hardware various types of graphics hardware developed, and all these fall into this category. However, now we have evolved into a graphics hardware which is mostly based on rasterization pipeline. However, the newest graphics hardware also again features ray tracing acceleration cores. So this hardware is typically used in either professional use in scientific visualization or in various real-time applications coming from various industries, not at the least from the gaming industry. Of course, virtual reality applications will be using graphics hardware extensively as well. The graphics hardware is a vector processor which executes the particular programmable pipeline in parallel. So there are many elements which can be processed with the same set of instructions in parallel. At the beginning, at the entry, we typically would have some geometry representation and some attributes associated with the geometry. And then at the end of the graphics pipeline, we would have a finally rendered image. And along this graphics pipeline, we will have various types of primitives on the way, and these primitives will be processed in parallel with small programs which are processing these primitives, which are called shaders. We will be talking about them in a moment. So the graphics hardware is really a SIMD, single instruction multiple data architecture of processors. Typically, it is realized as either as a dedicated graphics hardware, meaning which is attached through a bus to the main board and main memory and main processor, or it is also sometimes integrated within the main board as a coprocessor to the main processor. It typically has its own memory, which it accesses, and this memory access is very fast as compared to standard access to a memory on the CPU side. These various elements of graphics representations would be vertices, would be meshes which are formed by these vertices, and then an intermediate representation will be fragments, which are the rasterized elements of our triangles, and those are then projected onto the screen and processed with the shader program, as I mentioned. We can see here one example of a graphics pipeline where we have a 3D application which is using the graphics hardware, and then we are setting up a lot of various application-specific environmental settings with this and along with some kind of variables which we would like to send to the graphics hardware, along with the data, which would be the graphics geometric representations, vertices forming meshes, and these vertices then also being colored or equipped with texture coordinates. After this vertex processing, here typically the transformations, the viewing transformations and modeling transformations are taking place. Previously, a large part of the lighting calculation has been taken place here as well. This was because the Gouraud shading was calculated here and then stored as the shaded color on the individual vertex positions, and then it was interpolated along with other information in the rasterization stage. So we are having several stages which are not depicted here these days, and we will shortly have a glimpse on them, but we will be really talking about three main stages of, or two, in fact, of our graphics hardware pipeline. That will be the vertex processing and the fragment processing. There will be dedicated shaders. One is called the vertex shader and another is called the fragment shader. Those are sort of the main shaders you can use still these days, although there have been other shaders added to it. And currently there are also other types of shaders. So this vertex and fragment shader will no longer be in the pipeline because there are new shaders coming from hardware vendors such as NVIDIA. More about that in a moment. But the sort of central stage here of the graphics pipeline is really the rasterization. Once we have our geometric primitives, we need to turn them into elements which are projected on the screen, which we need to sort in the correct order, and we need to also interpolate those values from the points where we have this information available on the vertices. So information on the vertices is being rasterized in the hardware, which is then greatly accelerating the overall performance. This stage, rasterization, is in fact the only stage which is not really programmable. So every processing of our data around before or after can be programmed by the shaders, but the rasterization itself is not programmable. The API, which is related to graphics hardware, is often realized as a state machine. So we are often setting certain environmental conditions, if you like, and these are being set unless they are set to something else. And therefore, it is very important that we keep our code clean. And once we set certain values, we are aware of these values being set. And if we do not need them, then it's good to turn them off, because otherwise we might end up in an unknown state from the programmer's or the code's perspective. We see here examples of the OpenGL API, which we will be covering today, which has been in the graphics around since the beginning and is still widely used. However, there are other APIs also available for accessing the functionality of the graphics hardware, which are, for example, vendor specific, such as the DirectX API, or the latest APIs of Vulkan would be sort of replacing the OpenGL functionality and being one level on a lower level even than OpenGL graphics programming will be. It needs to be said that currently the graphics hardware is undergoing quite some evolutionary changes, because from the graphics hardware, also known as the GPUs, entirely new processor category has been born, or as an offspring, and those are all the tensor processors which are used for the deep learning applications. These are using the fact that the graphics hardware is highly parallelizable architecture, so operations such as convolutions can be implemented very efficiently there. So this means that the hardware as such is at the moment now splitting into two categories. One's type of hardware which is for the artificial intelligence applications, and the other ones which are for the graphics calculations. The graphics calculations are nowadays equipped both with the ray tracing and the rasterizer. This we will cover only the graphics rasterization stage, because this is rasterization approach, because this is much more used currently and delivers the code you will be coming across in terms of graphics hardware will be most likely related to the rasterization type of graphics acceleration. So let's have a look at the OpenGL. What is there? Let's start with just one simple command which you can find in OpenGL, which is a typical example of the OpenGL being the state machine. It sets the color if we want to clear our buffer, our display buffer, then we need to clear it with some color. And the color can be set, it's not automatically black, but here we are setting it to a black color where the R, G, B, and alpha are set. So this value is set, and when we will be clearing our buffers, then always this color will be used, unless we set the color to something else. And this doesn't sort of apply for the entire graphics hardware. This applies to one given context. So within an application, we will have a graphics context, and within that graphics context, we will have this state machine where all the states will be set. In parallel, on the same hardware, there could be some other graphics application running as well, and such an application can have differently set states. So while we really should see that the API is the state machine, but the graphics hardware is can hold or can be controlled by several states, by several APIs at runtime. So another example of a graphics API being the state machine is here. We can, for example, set that we want to perform the depth test which is the Z buffering. And here we even can define what is the depth function. So when should we discard a fragment as compared to what is stored in the depth buffer? Should it be in front or should it be behind the currently stored value? And there are many other state machine settings, such as stencil test, blending type, clipping, whether we want to perform backface sculling or not, whether the texturing is enabled, whether the MIP mapping is enabled, and so on and so on. Many states can be defined in OpenGL, and we will not cover all of those during just one lecture. This lecture will just give you one glimpse of the how to program a graphics hardware so that you will be capable of doing some hello world application, but it will take your own practice, your own learning or other courses to practice the graphics hardware programming even more. When we are programming for graphics hardware, we are executing a code at first on the CPU side. And the CPU, through the graphics driver and the operating system, are communicating with our graphics hardware, which is called the device. So we often talk about the host side, which is the CPU, where we define many things within our C++ code. And then on the GPU, we have our own dedicated memory to which we upload our information, and our own code, which is being executed, which are those shader programs, as I mentioned briefly earlier. So we might hear that about the host side, which will be the CPU code, and the device side, which is the GPU. The host, funnily enough, is often referred to as a client, and by that is meant the client application, which is running on the host. So the client side, in the case of graphics programming, will mean basically the same as the host, which will be the CPU code. The device side means it's always means that it's the GPU side where the program or the memory is being addressed. Graphics rendering is typically realized in cycles. So we are currently perhaps rendering one frame, and once that frame is rendered, it is being shown, and then we are rendering another frame. And while we are showing the previous frame, we are rendering the frame for the future. And this is realized in graphics APIs through the so-called double buffering, when we have one buffer, which is used for writing into, for while the rendering is being performed, and the other one is used for reading, so that we avoid inconsistency within our frame buffer, which will be both read and written. For stereo rendering, we would be then using 2 and 2 buffers, so quadruple buffering will be used. Very often, the refresh of these buffers is synced with the so-called vertical sync. This means that the drawing of on the screen will be synced with the way how the drawing on the screen is done on the actual display. That way, we will ensure that there is a consistent one image drawn and not that there is some kind of a tearing going on when half of the display is shown with a previous image and half with a new one. Therefore, we are enabling the VSync often. However, keep in mind that that also means that our frame rate, if we measure frame rate as a performance of a certain rendering application, will be also limited to the refresh rate of the monitor or of the display. So that might be misleading, and you also want to check, if you are interested in the frame rates, what is the frame rate if you turn off and disable the VSync. When we are performing the rendering, the often one operation which is done is to clear the buffers so that we have a black, or in this case, buffer to draw into, to blend with, for example, if the blending is on. This is not 100% necessary, but it is a good practice to clear the buffer before the rendering is done. In that way, we know that we are starting sort of from a certain background color. Also, we do not only need to clear the color buffer, but also the depth buffer. Because if we are doing the performing the depth test, then we might have the depth values stored in the depth buffer from the previous rendering, and then we will be also performing the depth test with the previous rendering result. So if we don't want to do it, which is often the case, we would be clearing the depth buffer for the given rendering cycle. You might ask yourself, why isn't this done automatically anyways? The answer is because we sometimes want to actually have multi-pass rendering, where we will first render something into the scene, and then we will be checking with our depth test whether we can throw something on top of that or not. And therefore, we would on purpose not want to clear the buffer between these multiple passes. So our rendering application can be, for example, realized in an endless loop like shown here. We have a while until we are closing the window, which is then triggered by the escape key. And in such a case, we will then be setting the closing the window to true. And but while this is not the case, we will be performing the rendering. And first, we will be clearing the color buffer, the depth buffer. Keep in mind that we can, in the clear command, we can have several buffers just concatenated with a logical operation, and because these are bits encodings, and with an OR we will then create a code which stands for both of these buffers. Then we perform the rendering, and once the rendering is done, then we are calling for the swapping of the buffers, and afterwards we are polling for some events, which might be some types of interactions. So this would be a typical scaffold for an OpenGL application, and in the following we will be looking more at how this part looks like, how does the OpenGL code then looks like in an application. I have mentioned that we are, before we will be talking about the vertex and fragment shader mostly, there are also other shaders which are to our disposal at this moment. The so-called traditional pipeline is starting with the vertex shader on the graphics hardware, and then we are performing the so-called tessellation shader, where we are in parallel tessellating more our geometry. So we might have some input rough geometry in the vertex stage, and in each rendering cycle we will be tessellating it, maybe creating a much finer mesh, for example, which is this stage, and also the tessellation stage. And also the tessellation evaluation shader. All three, we see that the light green shaders are those which are the parameterizable or programmable, and the dark green ones are not. So we cannot do anything about these. These are there and they just do their job. And we can see that the tessellation shader, the tessellation process is actually not programmable, but it's programmable from the tessellation control and tessellation evaluation shader. Then the geometry shader does something similar as the tessellation shader. It can also emit the geometry if we like to. But afterwards, that is followed by the rasterization. We will be using our rasterized primitives in the fragment shader or in the pixel shader, as it is called here. Pixel shader is the term which is used in the DirectX API. In the OpenGL API, we will be using the term fragment shader. The new pipeline, which is also based on rasterization, has a different type of shaders. We have here the so-called task shader part, which is the mesh generation. Afterwards, after the mesh is generated, then we have the so-called mesh shader. Afterwards, there is the rasterizer, and again the fragment shader. So here, the task and mesh shader are taking on the role of the vertex shader and tessellation shaders. There is a little bit different logic, but it is the geometry stage, which is the pre-rasterization stage. After this, we perform the non-programmable rasterization, and in the fragment shader, we perform the same operation. Let's have a look at the vertex shader and the fragment shader, how they can look like. We, of course, need to set them up properly from the host application, but then once we do it, we need also our shader program codes. And how do they look like is indicated here. These are the simplest vertex and fragment shaders. First, you are defining the OpenGL version, or GLSL version, which you are using, and which also then defines which syntax is then expected in these shaders. So this is the 3.3 GLSL core profile version, and we are starting with some input variables which are coming into our shader, which are stored in somewhere, which is called here location 0. This will be the vertex arrays, which I will be vertex array objects, which I will be talking about in a moment. But there is in the 0 location stored the vector of positions. So there will be all vertices which we need to have access to will be accessed through this location 0, and each position will be then defined by these 3 floats organized in a 3-dimensional vector. Well, the actual function of our vertex shader is shown here, where the main function does nothing else than passes these positions into a pre-defined variable, which is called the GL position, which stores then the positions of vertices for the further further steps along the graphics pipeline. You can see here that we are performing a slight conversion from a 3-dimensional points in space or vertices into a homogeneous coordinates. So we are here, our vec3 structure is then expanded by the homogeneous coordinate of the point and forming a vec4. This GL position is then used for our primitives, our faces, which are then rasterized. And after rasterization, we will be entering the fragment shader. Here the primitives will be represented as fragments, no longer as vertices, because we are after the rasterization stage. We also define the profile of our shader version, and afterwards we have again some variables which are defined. So here we can see this is the outgoing variable. You might see in the previous vertex shader that we have here an input variable, but we are also defining an output variable. So here we define that at the location 0, where we from the fragment shader always expect the color, there we will be storing it in the variable out fragment color. So everything which will be stored here at the end of the fragment shader will be the outcome for that particular fragment, which is currently being processed. We can also have a location 1, for example, and that would encode the depth, just to go a little bit ahead of the slides. The most simple pass-through fragment shader would be where we are just defining some color for all the fragments. So as you can see, we are defining some kind of greenish color here for every fragment which has been rasterized. But this doesn't go without any burden on the host side. On the host side, we need to define all our shaders, and also our shaders, fragment shader and vertex shader, and possibly the others, they need to be compiled into a certain shader program. So they need to be sort of stuck together, because the graphics pipeline expects a particular vertex shader and a particular fragment shader at least. So first we need to define our shaders, and here the first command is used in the OpenGL to create a shader. So we will get an outcome of this function will be a number which will define the number of our shader, and the parameter here is the shader type, whether it is the vertex shader, fragment shader, compute shader, or other types of shaders. Then we will be to this shader which we have created attaching its actual source code or replacing its source code, which we will be doing with this command. And once we have the particular shader indexed by the number which we have obtained from the GL create shader attached with a particular shader code, then we can compile it. And once this compiling goes without any errors, then we can use it in creating a shader program. So imagine that we have created one vertex shader this way, one fragment shader, as they were defined up in the previous slide, and then we will be putting them into one shader program. So we create first an GL program, so we again get some integer number which we use for addressing this program, and we can attach shader to this program. First the vertex shader, then the fragment shader. We link them in the program, and then in runtime, when we will be rendering, we define which program we are using, because we can have several programs prepared, and then during the rendering we decide which shader program we would like to use for that particular rendering pass. So now we have defined our vertex shaders, fragment shaders into a program, but we still do not have any data. We need data and the compute cores, so to say, on which the certain program is running in order to realize a graphics pipeline. This input data will be the input geometry, which is defined by arrays of vertices and indices, whether this could be just points or also lines as edges or triangles in various forms. We had these representations in the previous lecture, and these graphics primitives, these geometrical elements, can be also augmented not only by the position, but also by vertex colors, normals, or texture coordinates. So this information we will need to now somehow put together with our shader programs in order to realize the graphics pipeline. In the old days, there was a so-called immediate mode where we would have the GL begin and GL end as our drawing routine. And here in between these two commands, there will be all vertices defined which we want to render. So this means that all vertices will be defined on the host, and then they are, for each draw call, they will be sent up to the GPU and being rendered. Well, this is not very efficient approach, because you can imagine for large meshes there will be a huge data transfer to read all the vertices from the main memory and then passing them up to the GPU memory over the bus. There will be a lot of data traffic. Therefore, currently, we are using a different approach. We would like to, while there is still possible to somehow influence or change or map the data from the host side to the device side, often we would be just uploading certain geometry information onto the GPU and access it directly there. And typically we would use the vertex information which we are uploading onto the GPU. Imagine that we have a certain landscape and this landscape is not changing. So there is no point of sending this information over and over again from the CPU to the GPU, from the host to the device. So we can upload it once and then it will be on the GPU, and from that memory we will be accessing it. So that's the retain mode, which is more or less the common approach these days. And for that we are using buffers. There are many buffers which we could use for our computation, general purpose computation, but for particular tasks as well. Like, for example, the vertex buffer objects are those where we want to store the vertex information and vertex attributes as well. we will typically fill up the CPU memory. Some arrays will be formed on the CPU side or the host side, and those will be then transferred to the GPU with particular commands from the OpenGL specification. Also, if we would like to make sure that we can influence this data as well, we can have something called GLMap buffer operation, so that we will have always an up-to-date copy of the graphics hardware array on the host side as well. And we can also change it, and then it will be remapped onto the GPU. This will, of course, be associated with a certain performance penalty, but is in principle possible. And for applications where we frequently need to change these vertices, this will be also handy. There are also pixel buffers which are available to us. For example, typical will be a frame buffer and the frame buffer object, which are those type of buffers into which we will be rendering. And we can consecutively use these type of buffers as textures in the next rendering operations. Let's have a look at the vertex buffer objects, which store the vertex associated information. Here in these vertex buffer objects, we will be storing the position, always, at least the position. Sometimes we can add there the color, sometimes normals, sometimes texture coordinates. Any of these can be stored, or all of these can be stored in the vertex buffer objects. So these vertex buffer objects, their role is to transfer the information which has been generated on the host side onto the GPU. So first, we will need to define a buffer and generate such a buffer. Like, for example, we can see here. So we can create an triangle VBO will be one element array into which we will be storing our identifier of our vertex buffer object. So this triangle VBO 0 will be the identifier of our VBO, which we have generated with this command. Now, on the main memory side, we have a certain array which contains these numbers. These are 9 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. And while at this point they are it's just a linear array of numbers, we will be using them as 3 triangles. So there is a triangle. One triangle is minus 0.5, minus 0.50, and then another triangle is 0.5 minus 0.50, and the third triangle is 0, 0.50. How does it look like? Well, let's try to draw it. So we have minus 0.5 will be somewhere here, and minus 0.5 will be here. So that is 1 point on the triangle, minus 0.5 plus 0.5, so x. And then for the third one, 0 and 0.5. So that's the point, and this is the triangle, which we will be storing in this vertices array. But at the moment, it's just 9 numbers. What do we do with this array on the CPU? Well, in order to get it to the GPU, we will bind our VBO, which is here, and this VBO is then we will associate it with our main memory, and we will upload that information to the GPU. And that is done here with this command glbuffer data, when where we are defining the size, the array which we are using for uploading, and we also define that we are not going to change this buffer, that this buffer will remain constant. And after we have loaded this information onto the GPU, we are unbinding the buffer with defining that we are binding a vertex buffer object with an index 0. So that's practically unbinding the previous triangle VBO 0 buffer. Afterwards, on the main memory, we no longer need the vertices array because we have uploaded it onto the GPU, and therefore we can free this memory. Now, the vertex buffer objects were just serving us for making it possible to move the data from the CPU to the GPU. Now we have this information in the GPU, but we need the vertex array object for managing this buffer. And we manage it in such a way where we define which attributes are at which location. You might remember that we had this layout location 0 defined in the vertex shader and also in the fragment shader, but now these are vertex related attributes, and we will now be dissecting our buffer information on the GPU to define where is the information for the position, where is the information for the color, where is the information for the normal, etc. For now, we only have the positions. Our triangle doesn't have any color associated with it. It's just positions of 3 vertices, which we have stored and uploaded to the GPU. So what we can do here, we are defining our vertex buffer object. When in the VAO, we will have the particular vertex array object identifier defined. We will be binding it here, and then we are enabling the vertex attribute array 0. So that one is the one which we will be accessing from the location 0 in the vertex shader. And we need to know what we are putting there, whether it is a position or color or something else. So, and then we will be binding our vertex buffer object and picking from there where is this information which should go to the location 0. Well, we only have the position, so everything will be going there, but later on we will have examples where we will be dissecting this information from the vertex buffer object and defining where is what. So here we are performing the operation of defining where is the location 0 information, where we are starting. We will be starting, the offset is 0, and the size of our one element there, which is our vertex, is 3 times GL float, because we need 3 coordinates to define it. There are some other settings here which are not so much relevant, dealing with normalization, for example. The other one is what is the type of our positions, which float will be probably the most typical position. How many elements do we have? We have 3 because we are in 3 dimensions, and which is the location 0 that we are dealing with. Location 0 is specified here. After we have fully specified this, we can unbind the vertex array with binding the vertex array with the identifier 0. Once we have done this, we have filled the information of about vertices or loaded it onto the GPU and then performed the management of it. And now we have it managed in the vertex array object, which we have here bound. And then we can, in our retain mode, just have the draw call, GL draw arrays, and the amount of elements which we are going to render. So we want to render triangles, and we will be rendering three elements. We will be for that using three elements from our vertex array, because we only have the three elements there, three vertices. After the draw call is completed, we are unbinding the vertex array again. So here we can see our first pass through vertex and fragment shader in action along with the host code. So first we will be defining with our helping functions to get a window. So for example, the GLFW can be used for that purpose, and we have a window of resolution NX and NY. We are also within this window defining the viewport so that we have the information available for our last transformation from the normalized device coordinates to the viewport coordinates. And then we define our color, which we want to use for the clearing, and we will be loading our information about the shaders and shader programs. Once that is done, then we will be loading our data, which we first get into our vertex buffer objects and then into our vertex array objects. And then we have our endless loop until we hit the escape key here. And there we are first clearing the buffer. Then we define which shader program we want to use. So that's the with the shader ID, which we have generated previously. Then we are binding our vertex array, where the triangle is stored, and then we are performing the drawing. Once we know which computation should be done in the shaders, which shaders should be used, and which data do we want to use from those which are on the GPU, we can perform the draw call. Once the draw call is completed, we are unbinding the vertex array, we are unbinding the shader program, and then we perform the switching of the buffers, as we can see here. And we can then expect some interaction from the user. So you can see here what happened, that we have rendered our triangle with our draw call. The triangle was stored. We know what were the coordinates of the triangle. We have already drew them before, remember? So where this is the minus 0.5, minus 0.5. This is the plus 0.5 on the x side, and this is the 0.5 on the y axis. So, but why is this triangle now green? Well, because in the constant fragment shader, we had this green color. So not everything is green. This you can consider as black, because we have cleared the buffer, and we have rendered in that buffer only one geometric primitive, this triangle, and rasterized it. And this rasterization has led to assigning for each fragment associated with this triangle to give it this olive type of color, which we have done in the fragment shader, and we can see here the result. So this is how a simple graphics hardware program can look like, where we are using the rasterizer, which we have already learned how it functions, and we have also implemented it, or are implementing it now for our assignment, but we can use it by the help of the graphics hardware and by the particular API, in this case the OpenGL. Naturally, in our graphics pipeline, we need to deal with some transformations of our objects or of our scene parameters, such as camera or the lights. And for that, we would be using the transformation matrices quite often, and we need to somehow put them into our fragment and vertex shaders so that we can use them, primarily to the vertex shader, because there the viewing transformations will be happening. Now, we have in the previous versions of OpenGL, the matrices were directly supported, and we could use the push and pop operations for performing hierarchical operations. But this has been now deprecated from OpenGL, and some external library needs to be used for handling matrices. Now, we would need for the vertex shader to define the following vertices. First, the following matrices. First, we need the transformation matrix from the object space into the world space. And then we need the matrices for the viewing transformation. And you know that this is a concatenation of several vertices, bringing us from the world space to the camera space, from the camera space to the normalized device coordinates, and from the normalized device coordinates to the viewport coordinates. So therefore, we would need to deal with some of these matrices on the host side, and then also on the shader side, and we need to on the device, and we need to somehow connect this. And this will be connected through the so-called uniforms, which we can change every time we are performing the draw call. So we will be sending them from the host side to the device with every draw call. But this is just a small fragment of information, so there will be no noticeable penalty in terms of the performance. Let's have a look at the GLM library, which offers us somehow the mathematics structures for OpenGL. So we can, with having the GLM, we can have these following data types, such as vec3 and vec4, also on the host side, mat3 for 3 times 3 matrices or 4 by 4 matrices, all equipped, all these structures in floats. And then even we have some transformation matrices or rotation matrices, which are generated right away for us, all also scaling vertices. So we will be putting in the parameters for these transformations, and the outcome of these operations will be the corresponding vertices which we need. Also, there is a support for the viewing and projection matrices. So this is GLM lookat will be creating a matrix based on our eye position, our up vector, and our viewing direction. And GLM ortho will be defining our orthographic projection, or GLM perspective will be defining our perspective projection. So all this is available in the GLM, which could be used. One could implement it on his or her own, or use a different support of math structures for OpenGL. We will be using here for these examples the GLM for on the host side. So we can define our orthographic projection, for example, with this function, and this function will create as a matrix, which will be a 4 by 4 matrix, and this will be our projection matrix, where we can see that our top and bottom, left and right, and near and far information is stored here in this orthographic projection, and the outcome will be our projection matrix. So this is stored here on the host side, and also we will be having in the same variable name, but doesn't need to be the same name, is also used in the vertex shader. So we already know what these parts of the code mean, and now we have this uniform, which is of mat matrix, which is 4 by 4 matrix, and the projection matrix, which we have filled on the host side, is here available in the vertex shader through this uniform. And what we will be doing with it, we will be simply performing a projection matrix calculation or multiplication with our vertices. So we will be performing orthographic projection of our vertices onto our viewport, and in a way that we will be multiplying these vertices with our projection matrix. We can have here more multiplications with the camera positioning or with the model matrix, but for now we have only the projection matrix multiplied here. Okay, so this is how we can get our uniforms so that they can influence our shader programs. Now just a simple vertex shader. And how do we set up the code so that we can actually get that information into the shader? Well, we have defined our projection matrix here, and then we will be defining a mapping variable, which will be defining which one is our uniform. So here we will get an identifier of our uniform in the shader, which is having the name pro matrix. So from the shader, so in the shader. And we will get some identifier for this variable or for this uniform. And then one at runtime, just before we are issuing the draw call here, we will be mapping onto this uniform and another its values of this matrix. So here there are the values of the matrix which has been defined on the host side here, and as we are storing it in this mat4 structure in order to get the pointer to the data, we need to access it in this way. So we have now uploaded the matrix onto the GPU, and just before binding the vertex array objects and the draw call. After we have performed this, we will be unbinding the vertex array object and unbinding the shader program, which we have as the first bound here. So this is the simple way how we can interface the shader programs with uniforms, and those could store any information which could be somehow useful for us in the computation. So for example, if we will have now for our representation, we will not only have for our single triangle only the position, but we will also have its color. Now our triangle is having a little bit different coordinates, but this will be these first three numbers will be its position, and then the second three floats will be its color. So 110 will be RGB. So this color will be something between red and green, which will be the yellow color. And then the second vertex defined here will be having the cyan color. And then the third vertex here will have the red and blue, so it will have the magenta color. So we should look for these colors at the vertices at some point in time once we'll be successfully rendering this type of code. So here we have just created on the host side a structure of an array. So this is a one-dimensional array which has now not 9 elements but 18 elements. And again, in the same way, we will be binding the vertex buffer object, and we will be filling this information into this vertex buffer object. And now we will be binding it for the purpose of managing it. So we will put into our location 0 the positions, and you can see here that the there are three positions of float, and we don't want to normalize, and the size is now it starts at the 0 position, the first position, and the stride. So how many elements do I need to sort of jump over to get to the next set of positions is 6 times size of geofloat. Of course, we will be reading the first 3 for our positions because we have here three positions defined and geofloat as well. And then we will be skipping the other 3 floats, which will not be in the location 0 because those will be in the location 1, the color attribute, which is defined here. And here we will have the same thing. We will have the vertex attribute pointer command executed now for the location 1. Again, floats, 3 floats, but this will be now related not to the position but to the color. Again, not normalized, and the normalization might be handy for example, normal. And then again, the stride, so how many, what is the interval of our information per vertex, so to say. And what is the offset? Where do I start? So here I am saying that my pointer to the first element is after the first 3 floats. Of course, because the first 3 floats will be my position here. So if I want to relate to the color, it should be after these 3 floats. Now, you might ask yourself, why do I have to have this array so interleaved? And the answer is that it is good to have it interleaved also in the vertex buffer object, because if I want to access a certain vertex, I want to access its position and color, and this information needs to be therefore stored next to each other in the memory. So therefore we have this linear array where these things are stored next to each other. But if we want to deal with them and manage them, we need to dissect them into these different vertex attribute arrays. And then we will have the position in the location 0 and the color in the location 1. If we look at our vertex shader now, we see that we have here location 0 are the positions. This is the incoming variable. Here is the location 1 where we have the color. But the color, we do not want to have only for the vertex shader. We would like to pass it on to the fragment shader. And therefore, we are defining the outgoing variable vColor, which needs to have the same name in the fragment shader as an incoming variable. So they need to have the same name so that they can be matched. And then we are performing just defining that the in color, which is the input color from this vertex array object, is then passed onto the vColor variable, and this vColor variable will then be in the rasterizer rasterized so that we can, for each fragment, access an interpolated value of this vColor. Then we are as the last command in the vertex shader, we will be multiplying our positions with our projection matrix and storing it in this built-in variable GL position. In the fragment shader, we are then having access to our vColor. And now our fragment shader is a little bit more complicated than the one before, because our outcome stored in the location 0 is not just a constant color, but we actually fetch this color from our vertex attribute objects. And this color is also then interpolated through the rasterization process. So we can see here that while we have our v color is a three-dimensional vector for our um, uh, built-in location 0, it is expected to be a vec4 variable. Therefore, we need to create it a vec4 with the alpha component, which will be equal to 1. And once this is done, we can observe our rendering and we can see one vertex is yellow, one vertex is cyan, and one vertex is magenta. And there is a nice interpolation in between using the barycentric coordinates. So we have actually created something what we intended to do at the first place, and the code, this following code has realized this simple hello world OpenGL graphics hardware accelerated rendering. If we would like to have a little bit nicer representation on the host side of our array, and possibly which is also subject to change, we can use a structure where we are having the first part will be the position of defined as a float three-dimensional vector, and the second float three-dimensional vector will be the color. And we can create the standard template library vector, which will have this vector of such a structure, which will be then stored in this model data variable. And this model data variable will then be used in order to fill the vertex buffer object here, where we access it through this model.data, which is the way how we will access the information, the data stored in this standard template library vector structure. Now let's have a look at a more complex code, more realistic code of a shader, which is still not very complicated, where we are realizing our blink-fong illumination. So this is therefore some part of the operation is realized on the in the vertex shader, and some part of this operation is completed in the fragment shader. As we know, the blink-fong illumination is not calculated per vertex, but per fragment finally. But some information can be passed on from the vertex shader and can be rasterized before it is then fetched in the fragment shader. We have to keep in mind how is the blink-fong vertex shader to be realized, and in which space we can actually calculate it. We have previously calculated it perhaps with the ray tracer, and this was not a problem. Then we have, because we were in the world space and we were calculating this illumination in the world space. But in the rasterization stage, the question is along the viewing pipeline, in which space are we going to calculate this illumination? We can calculate the illumination in the world space or also in the camera space, because in the camera space we are just having simple transformation, but we are not performing any non-uniform scaling or something like that. Therefore, we can, in the vertex shader, we will be calculating our information in the camera space, which is relevant for the illumination. So let's have a look at the code. We are again having the position and normal in our location 0 and location 1, and we are filling them into our vec3 variables for the position and the normal. So now the normal is the second one and not the color. Previously we had the color available. Now we want to pass to the fragment shader the normal, which should be a vec4. Then we want to pass on the halfway vector and the light direction as well. Now these three are going to the fragment shader, and we want to have them rasterized so that we can use them then for the illumination. You can see here that we have some structure even defined in our uh, shaders, and we have here light where we have access to its position and the intensity. On the host code, we will be then defining the handlers with these parts in this way, where we will access the structure elements through the dot operator and search for the variable with this name. So we have the variable is here, our uniform, so that we can change the light at every position, position of the light at every frame, and also its intensity if we like to. Then we have other matrices available. So we have the projection matrix, we have the viewing matrix, we have the model matrix, and we have the normal matrix. What is the normal matrix? That is the matrix which we want to use for transforming the normals. Remember, we needed the different matrix for transforming the vectors, then transforming the points back then in the transformation matrices lecture. And in our vertex shader, we will be first calculating and transforming our positions. So we have our positions stored here. Now it is changed into a homogeneous coordinate. First, we perform the model transformation because it was in the object coordinates. Then we are performing the viewing transformation, and this way we get our points, our positions are in the camera space. In this camera space, we are, or eye space as it is called here, these terms, as you know, are used interchangeably. We are also transforming the light positions. So light position is the vec4, which will be going to the which is then used for the light direction vector, is calculated here, where we have the light position information in the world space, and from the world space we are transforming it with the viewing matrix to the camera space, to the eye space. So now we have the light positions in the eye space. We are the normal, which is associated with our vertex, will be also transformed, but not with our other matrices, but with our normal matrix, which we have, which is the one shown here. So this was the transformation matrix, which was the inverse and the transpose out of that, as you might remember. Now, for our blind Fonck, we need the following information. We need the, so if we have our surface, we would need at a certain position, we need the viewing direction. So that would be the direction, which is the minus pos. So we are in the camera space. The pos has been is the position of the vertex in the camera space. And if we want to change the direction from the point on the surface towards the viewer, then we need to negate this vector, and we normalize it because we want to have normalized vectors for the illumination calculation. The light vector is here, so, and we want to calculate it as the light vector position minus the position, which means that from our vertex on the surface, which is the position, we are then subtracting the light position to obtain this vector. And we again normalize it here so that we have the normalized light vector. And then we also need the halfway vector, which is the halfway vector between the V and the light direction, which we are calculating here. So we are summing them up and normalizing them to obtain the halfway vector. So that will be, the halfway vector will be somewhere here then. And finally, and now you can almost not see it anymore, finally, we will be performing our projection, because so far we got our vertices to the camera space, but we, at the end of the vertex shader, we want to also perform the perspective transformation. So this is, or the projection transformation. So we are multiplying our position with the projection matrix, but we do not want to perform that on the calculated vectors which we obtained here. Therefore, we first get ourselves into the camera space, and then we obtain all the necessary information, the halfway vector, the normal vector, and before we then get our position into the normalized device coordinates with the projection matrix. Okay, so we have now calculated the light direction, halfway vector, and also the normal vector, which will then be rasterized, and we will have access to these in the fragment shader. So this was the vertex shader of the blindfong, where we calculated the halfway vector, light direction, and normal. And now we will go to the fragment shader. In the fragment shader, we have these vectors available at our disposal. However, those are has been interpolated, which means that even if I have a unit normal, for example, at one position of my triangle, and here is another one, if I interpolate, and here's my edge, for example, then these vectors will not be unit vectors. They will be shorter a little bit because I performed component-wise linear interpolation during the rasterization. So I will need to make a unit vectors out of these again in the fragment shader. More about that later. So again, we have our structure for our light, where in this structure we will be this time only using the intensity, not the position, because the position we already have available for us from this light direction vector, which we calculated in the vertex shader and then rasterized. So, and after, besides that, we have few more uniforms which we can use here, which are the ambient illumination coefficients, the ambient illumination intensity, the Phong exponent, for example. And here in the function, we then just perform our Blin-Phong shading. So we normalize all these vectors first normal vector, halfway vector, and light vector, and then perform the illumination, where we have the ambient term here, then we have the diffuse term here, where we are using the light intensity, as you can see, as the uniform from this structure light data, where we need our light direction and the normal for the diffuse term. And then for the specular term, we again use the light intensity here, the KS uniform, and in the dot product, we are using the normal vector and the halfway vector. The uniform of the Phong exponent is also necessary here for the calculation of this power function. And at the end, we get the final intensity value, which is then stored and in the fragment color and then stored in the frame buffer. So this is how we calculate the blink-fong shading, partially in the vertex shader and then partially completed in the fragment shader. On the host side, we need to set up all these uniforms. So we first perform calculations of our. So we are just before we are issuing the draw call, we define which program we want to use. So this is the blink-fong shaders, vertex and fragment shader in this shader program. Then we are calculating the modeling transformation, which will be now first identity, and then we will be performing some translation, and then we will be performing some rotation of our objects so that we have something in the modeling matrix. Then we are calculating our normal matrix, which should be used for the transformations. And this normal matrix is, as we know, is the inverse and transpose of the model matrix and the model view matrix. So this is the normal matrix, and then we are putting or identifying the individual handlers, nmat ID, pmat ID, vmat ID, mmat ID, with the values which should go into these matrices, which is shown here, where all the necessary matrices are passed on to their shader counterparts. So these are the matrices which we are then using in our vertex shader. And then we have, for the illumination, the diffuse coefficients, ambient coefficient, and specular coefficients. And then we have our Phong exponent here. And once we define these, we need to again map them on our shader uniforms, as we have done here. Once this is done, then we bind our data, and once we have bound our data, then we can perform the draw call with all the uniforms and the data and the program set up as we want. The draw call is completed, then we unbind the vertex array and unbind the shader program. We do not need to only perform shading in the fragment shader. We can do there anything we want. So, and in order to be able to understand, for example, whether our rendering is correct, then we can perform a normal shader. So here we do not only have just one triangle which we are rendering. Now we have here 3 copies of a dragon mesh, and which is consisting of many triangles, this mesh. And now here we are in the fragment shader, while we have somehow so here we are having our fragment color, vec 4, and we are filling into this fragment color the actual normal, which is then normalized. So we have it between, it's a unit vector, and we are multiplying with it the 0.5. So our normal can go between -1, 1 for each component x, y, z. So we are bringing this, scaling this into, for each component, -0.5 to 0.5. And then we are adding the 0.5. So we are remapping it to 0, 1. And this is what we have calculated here as the intensity, which is not really a shading, just the calculation of the normal. And we can put it into the fragment color. And with this, we will be then able to see the normal buffer on our geometry, and we can debug whether the normals look right or there is some problem with the normals. Often, we might also use such a normal shader for calculating the normals, and then we will use in multipass rendering this information as a texture so that we can compute an intensive calculation of the shading based on this normal buffer. So we will not sort of shade every fragment, but only those which have been in the previous depth test evaluated as being the frontmost. By that, we will save some computation time, especially for the scenes which will have a lot of fragments which are drawn, but finally they are not visible because they have been overdrawn by some other fragments. Finally, we also can use in our vertex arrays textures and as texture coordinates and associate these texture coordinates with a particular texture. So if we want to set up a texture, we will then have some image buffer, which will be float array of dimensions of height and width, and it will be 3 components RGB. And this image will be then either imported from some existing image or some procedurally generated image. And once we have that, then we can generate ourselves a new texture and have a new handler of this texture stored in the texture ID. Then when we bind this texture, we can define various parameters to it. So for example, what do we want to do outside the range 0 and 1? So if our texture coordinates are, for example, -3, -3, what should happen? And that can be defined as GR repeat. So this is the 0 and 1 range of our texture for X and Y coordinates. And these are the negative coordinates. This would be the positive coordinates. What should happen there? So with GR repeat, we are defining that we will just repeat that texture over and over again. With mirrored repeat, we will be mirroring this image in these other replicas, if you like, repeated replicas. We can have other forms of what to do with the texture, how to wrap it with the clump to edge, which we can see. Here is the image, and then the last column or row is then propagated further. Or we can have clamp to border, where we will have just the image and then background color used for the or the border color, which will be then repeated. So we are defining it here for both the for S and T, for both the U and V parameters of the texture, and then the next parameter will be whether the magnification filter should be nearest neighbor or linear. So we will want to have a smooth magnification filter. You know it from the lecture on textures, that what to do in case of magnifying. So we want to have a bilinear interpolation, and the same for minification if there will be the opposite situation to the magnification situation, where there will be a lot of texture sort of stored at one fragment. What should we do? And there will be also the bilinear interpolation set for this case. These are the parameters for defining the behavior of the texture. And finally, we can load the texture from the main memory on the host side to the device side. So here we have our image data, which we have previously filled with some information. And this is a two-dimensional texture. It is an RGB texture. It has 3 components. These are its dimensions. And there are some other parameters to this command, like that the individual elements are floats, etc. After we have loaded this text two-dimensional texture image, we can unbind this texture to the handler which we had before the text ID, and then we can also delete the image data from the main memory because it's already on the GPU memory and we do not need to store it at the main memory as well. Once we have this texture stored, we still need to somehow get the texture coordinate for each vertex. So now our structure vertex data will have position, which is a three-dimensional vector, normal, which is a three-dimensional vector, and texture coordinates. Three floats, and two floats. And we can see it here. Three floats, and two floats. And once we of course load the entire array of this or vector of these structures on the into the vertex buffer object, and then we need to define at which location we find which information. So at the location 0, we will be finding our positions with the offset 0. And here the stride will be 8 times size of float. This is one float, second float, third float, fourth float, fifth float, sixth float, seventh float, eighth float. So our stride is 8 floats, while the first 3 will be our position. For the location 1, we will be storing our normal, and that will start with the offset of 12 bytes. So we have the GL float. Each float is 4 bytes. So 3 floats for the position we need to skip if we want to access the normals. So this is all defined here. The stride is the same. And for the texture coordinates, we need the position 2. And here we will be having the offset of 24. So 6 times 4 is 24. And the stride will be still 8 floats. So we have organized our vertex buffer object into this vertex array object, and then we can unbind the handler and this vertex array once we have managed it. And now we have pretty much everything we need if we want to perform some texturing and shading of one of our geometry. This will be the plane on which these dragons are sitting, which we will texture with this texture here. So for that, we need to set up the texture on the host side. So remember, we have just defined the texture, but now we need to define an identifier with which this texture we will access in the shader. So in the shader ID, we need to define which texture unit we will use for binding our particular texture. So our texture is bound here in this handler, and in this case we will be filling out for this texture unit ID the value 0, because our texture will be associated with the texture unit 0. We have set this active texture unit here, and there we will be able to find our texture which we have previously filled. Then we are performing with our vertex array objects the same. We are performing our draw call of our triangles, and then we will be performing the unbinding of the vertex array and of the texture. We will associate the texture with the handler 0, which means we are unbinding the texture. And also we are unbinding the program. In the vertex shader, what we will obtain our texture coordinates through the location tool. Remember, we will be defining an outgoing two-dimensional vector for the texture coordinates, and these will simply just take in the texture coordinates which have been in the vertex array object and passing it to the rasterizer so that these are rasterized, and then we have them available in the fragment shader. In the fragment shader, we will be defining a sampler is the uniform for texture units. So we know that our texture unit is now sampler has value 0, and so this is stored in this texture unit variable, and then we will be sampling our texture, which is stored in the texture unit 0. So here is the 0, and we will have our texture coordinates, and we will obtain at our sampling position of the texture an RGB value from the texture. We will store this information in the KD texel. So this is the diffuse term will be not using the color of the vertices, but actually the texture. And when we are performing our illumination, we will be having our ambient term, and for our diffuse term, we will be using the color obtained from the texture and illuminated, shaded with the previous methods which we have already described with the blindfong shading, and the specular highlight will be there as well. However, that one will not be using the colors obtained from the texture because the specular highlight will be independent from that. And this way, we can then expand our graphics hardware rendering into illumination and also usage of 2D textures. Well, that will be all for today. This was supposed to be just a sneak preview of how graphics programming with a certain API looks like. I hope this was understandable for you. More information you can find in the chapter 17 of the textbook which we use for our course. That will be all for today. Thank you for your attention and see you at the next lecture.